Now let's take a look at some more graphs and displays for data that we've collected. In looking how to graph out quantitative data, the stem and leaf plot is another way for us to collect, organize our data, and display it in a way that we can see how it's distributed. The results of a stem and leaf plot is something similar to a histogram, kind of a histogram turned on its side. But regardless, we can still see which classes or categories have the highest frequencies and that type of thing. One thing that separates the stem and leaf plot from a histogram is that we can still extract the original values by looking at the stem and leaf plot. And it also provides a really quick and easy way for us to sort data and organize it from lowest to highest, which is, for a large set of data, is actually fairly, without technology, difficult to do. So in a stem and leaf plot, we have one side which we call the stems, and then the other side we call the leaves. So we look at our data values, and we can see here that the data is going from 21 up to 45. So we take the first digit as our stems. They basically run from 2 to 4. And then along here, we put, for 21, we put a 1. For 25, we put 5. Notice if we have two of the same number, we just put another 5 there. 26, 27, 28, 30, 36, two 36s, and then 145. And we can see that the data is very right skewed, with most of my data here in the 20s. So here's another data set that we can look at. Let's see if we can begin constructing this. We want to look for what is the lowest value that we have here, and it looks like it might be in the 20s. Do we have anything below that? Oh, here's something in the teens. I think that might be the lowest. And then the highest numbers appear to go all the way up to 149. And I believe that's the highest number. Okay, so in looking and constructing my stem and leaf plot, I want to draw a line. My stems will be over here, and we're going to start with 1s, and we're going to go all the way up to 14. And notice that whether or not I had, for example, any 130s, I'm not going to worry about that. If I do have anything, I'm just going to leave them blank. Okay, so I've created my stems. Now we can systematically go through, and in this case, I'm going to go by column. So I'm going to start up here, and I'm just going to go down from there. So I have a 76, so I'm going to place a 6 next to the 7. 122, so next to 12, I'm going to put a 2. 66, 76, 41, 26, 33, 29, 23, and 38. Notice that I'm not worrying about the order of my leaves here yet. And I'm not trying to just find all of the teen ones, the ones that have a 1 out front, and then go through and try to find all the 2s, because most likely if you do that, you're going to skip over numbers. And I'm not worried about the order of the numbers yet. If I wish to put them into numeric order, I can rewrite it really quick and easily with my with my leaves in numerical order. Continuing through this, here's what we end up at the very end. We can see that, the vast majority of my data is here on the left-hand side, which means my extreme values are over here on the right, making this a right-skewed distribution of these values. And these are text messages sent in one day by 50 cell phone users. You'll notice that the numbers are out of order, but it doesn't really matter as far as if I'm just trying to get a good look at the distribution, the shape of the curve that I have here. If we twisted it on its side, we would have kind of that histogram shape. And I went through and I counted all the numbers to make sure that I have the same number of numbers as we have here, which is 50. And I at least have that as a confirmation. That doesn't mean that I didn't make a mistake somewhere along here. But But I also did notice that there was a 16, which I didn't see before. Where's that other 6 there? It's the 16, which I thought 19 was my lowest number. But there was a number hidden in there. And that tells you how difficult it is. Here's the 16. To see those sometimes. They just kind of hide in plain view. If I rewrite it and put it into order, it's also important to put a key here so that we can see what we can interpret this correctly. And if they're in the thousands, maybe this is representing home prices. So 10/2 could mean 102,000 or something to that effect. At any rate, you would display that here in your key. And this just gives us a good idea here. We can see that more than 50% of cell phone users sent between 20 and 50 texts. So if we go from here to here and count those values, we can see that comes out to about half of the data. So there's a lot of observations here that we could make with the data that tells me something about the underlying numbers that we had, which before were just in a big spreadsheet. Another way to organize the data is to do, and this really applies when we have a large set of data, is to do 2 stems for every thing. So for example, for our data, just if I was going to get a start here, we do 2 1s and then 2 2s and 2 3s and go all the way down to 2 14s. And the first one, like this, would be 10 through 4. So, 10 through 14. And then here we would have 5 through 9. So what this does is it divides up, especially if we have a lot, and spreads it out more. So you do the 0 through 4s with the 2, and then the 5 through 9s with the 2s, and with the 3s, et cetera, et cetera. And we can just get a different view of it. You can see, even though there was nothing that was below 16, we still left that other one so that each class had 2. And sometimes you're going to have gaps, but even the gaps tell us something about the data. It kind of separates those odd ones, sort of what might be considered outliers from the regular data, and just gives us a view. So we can compare this to this. Very similar shape, but maybe a little more spread out. This is especially true if we have data values, like in this case, our 2s and 3s happen to be pretty long. It just helps minimize the heights of them, but still gives us an idea of where and how our data is spread out. Another type of graph that we can do is called a dot plot. And this is different than a scatter plot, where we're actually going to look at that as well. But with a dot plot, we just have every data plotted along a horizontal axis. And if we have anything that's kind of in between, we stack them on top of each other. So we had 2 25s, and so they're kind of stacked, or they should be stacked above 25. These are shifted a little bit for some reason. So we had 2 25s, we had a 21, we had a 26, 27, 28, 29. I think this is supposed to be 30, actually. Somehow these have been shifted a little bit in this particular picture, but you get the idea. Any repeating numbers, we just put them on top of each other. And so here we can look at the same data that we just analyzed, and we create our horizontal axis. Notice that each of these was 5 values away from each other, and we kept that consistent, which is what you want to do. Gaps are okay if there's no numbers within those gaps. We don't want to have them there. And we just put dots above the values as they appear. If they're in between, so we have a 66, 67, 68 type thing, we just kind of estimate where they're at. And any ones that are repeating, we put above each other. But you can see, especially with my doubleized, when we doubled out the 1s and the 2s and all that, it looks very similar in the shape. Of course, this is horizontal, the other was vertical, but regardless, it does give us an idea of where most of the data was centered, and then some of the scattered ones as well. Taking a look at a time series, a lot of times we want to look at trends over time. Think about stock market and that type of thing. A lot of times every day they're going to give you a rundown, and every 5 or 10 minutes you'll see where a stock value is at. And so in a time series, we're plotting dots over time periods and then connecting those dots with their various heights. Here we want, and what we're looking for are trends, trends that we see over time. So here we have motor vehicle thefts, and we also have burglaries. Of course, these are in millions. And as we put them across our time scale here, with each year, whatever its value was, we put a dot for that. Then we connect those dots to see kind of a free, smooth, flowing curve. And what we're looking for are trends over time. Another graph you're probably familiar with is a pie chart. We use this for data that's not quantitative usually, but for qualitative data, data that is non-numerical in nature. And it's a good way for us to show the percentages of data and compared with the whole. And we divide the circle into sectors that represent categories, and the area of each sector is proportional to the frequency of each category. So if I was looking at degrees earned, again, this is qualitative or categorical data, and these are in thousands, and this is for the year 2014. A pie chart is an easy way for us to organize this. To organize it, we're going to use the central angle that will correspond to each category. To find the central angle, we're going to multiply the relative frequency by 360. So for example, the central angle for associate's degrees, here's the relative frequency of that, about 26.4%. And if we multiply that by 360, we see 95 degrees is going to be the central angle. Oops. If we do that for all of them, we can see, for example, my bachelor's here is just a little bit short of 180 degrees, which would be a completely straight line. It's 177. There's our associates, which is just a little bit more than 90 degrees. Doctoral and master's, at any rate. These are best, unless you've got a way to measure angles like that, like a protractor. These are best done with a computer or some sort of technology. A bar chart is another great way to display qualitative data. And if we put that data from highest to lowest, we call it a Pareto chart. So rather than a bar chart, they give us this fancy name called Pareto, which is simply just putting them, since there's no order, because they're not really representing numbers, they're representing categories. We can tell that this one here would be our bachelor's, or maybe it was associates, then bachelor's, then master's, then I'm trying to remember. Nope, bachelor was the biggest. So we would have bachelor's, then associates, then master's, then doctoral, right? So we put them in order of decreasing height with the tallest bar over on the left. That's what makes it a Pareto chart. Otherwise, it's just a bar chart if they're in a random order. So here we see another example of heart disease, cancer. These are top 5 causes of death in the United States. Respiratory disease, accident, stroke. And so from this, we can easily see that the leading cause of death was heart disease. And this is deaths in the thousands. Of course, if this was this last year, coronavirus would maybe have competed with either of these as the top killer. But this is from 2014. And it also, we could compare these number-wise and see, like, even if we added these up, this still is more deaths than all 3 of these later ones combined. So this is all interesting information, numbers put into a picture form to help us organize and make sense of data. We also have paired data. This is where we have not just one set of data, but we have 2 sets of data. and they correspond with each other. So every X has a corresponding Y. If we have two sets of data where we have an X and we have a Y, we can do what's called a scatter plot. And we just simply put out points, and each of these points represents a data value. We plot those on an XY curve, and what we're looking for are not exact relationships, but approximate relationships that we see as we move along the x-axis. So just to give you an example of what we're talking about, a British statistician, Ronald Fisher, introduced a famous data set called Fisher's iris data set. The data describes the various physical characteristics, such as the petal length and the petal width in millimeters, for 3 species of iris: the petal lengths from the first data set and the petal widths from the second data set. So with this particular plant, we see the x's would be the petal lengths, so that's my x-axis, and then the petal widths are along the y-axis. Each petal, we record that, and then we plot it out. And what we can see trend-wise is that we have a pretty linear trend. In other words, it's kind of making a line, if you pictured these, not exactly, but in a bit of a straight line here, as far as the pattern. And so as the petal lengths are increasing, we're also seeing the petal widths increase as well. And that's what what I read was actually just right here. So the scatter plot we use when we have 2 sets of quantitative data. We're going to revisit that down the line here.